All right, so starting on chapter 7, our summary introduction to the solar system. Okay, so our chapter plan and the three parts of this lecture and the slides are key planet characteristics for number 1, classification of bodies for number 2, and the solar system history. Both a summary and a discussion of how that history is dated. And if you are wondering what we mean by key planet characteristics and classification, hopefully that will become more clear. Uh, Namely, it's about separating the planets into different categories. All right, so let's describe some key characteristics. And here we're really just defining terms. Okay, so in this part of the lecture, let's make sure we are all on the same page for some concepts, namely the ones listed here: size, density, orbital period, rotational period, orbital tilt. A lot of this should look like review because we've seen it in the previous chapters, mostly chapters 1 through 4. And I suppose a little bit of some of the physics background material as well, although nothing about light, so not so much chapter 5. Okay. So, by the way, I think size is pretty clear, mass and radius. We're dealing with approximately spherical planets. So I will take a quick minute and point out that if you do have a defined radius for a sphere, which I'll draw in cross section, so this is your radius, then the size of that planet can be described by its volume, where the volume is that of a sphere, which is 4/3 pi r cubed. Don't have to memorize it. It'd be given if you were ever asked to use it, uh, up to the point of maybe a concept question. It asks you to know some idea about how volume is related to the radius. But for an actual numerical question, the formula would be given to you. So I guess you could say that you need to know the proportionality, that volume is proportional to the cube of radius, but the 4/3 is easy to forget. And even though, you could Google it for the homework, it would be given anyway. And for an examination, you'd be given the formula. And then if you need to relate volume to mass, this is nicely related to the concept of density. And I'm just going to quickly point this out because we'll see some more ideas in the next couple slides. But the mass represented by uppercase M in this case, could be lowercase m, but we usually use uppercase M for planets. Well, then you would have the relationship between density and volume. And it turns out that mass is simply the product. So we would take the density, which is represented by this letter that looks a lot like a P and is the Greek letter rho, and that's the variable, the letter, but the variable that is used for density pretty much exclusively. And we'll put it down here that is, if we are writing an equation that involves density, we would use that letter, and it is spelled RHO and pronounced row, kind of like row your boat. Okay. And orbital period, that is the time to orbit the sun, just to run through these because I hadn't yet. And where have we seen that before? Think Kepler's third law. Okay, so that's the same orbital period that shows up in Kepler's third law. Rotational period is the time for a planet to spin on its axis. So not an orbit around the sun, but rather a spin. The other term for orbit is a revolution. So revolution and orbit are synonyms, but a revolution is not a rotation. And so those terms have very specific definitions. So revolution, right here. A revolution, orbit, interchangeable. but revolution not interchangeable with rotation, even though they are in everyday speech. You say, oh, something's revolving, it's rotating, kind of means the same thing. But here we need to distinguish between them. I kind of will try to use orbit when I talk about revolutions, but this term, I may use this word, which is why I'm mentioning it now. Orbital tilt, well, that's like the tilt that causes the seasons on Earth, which we know for Earth is 23.5 degrees. That is kind of a key characteristic of planets. So more about density. All right, so density is the amount of mass in a specific volume. Okay, so it's the mass per volume. Okay, well, here's a question for you. If you have 10 kilograms of feathers and 10 kilograms of bricks, which is more massive? Not asking about density. We'll get to that. Here, I'm just asking about mass. Thank you for the answers. And I have bad news for you, maybe annoying news. It was a trick question. It was none of the answers. So how are you supposed to know that? Because typically, right, it's one of the options. Well, it was just to make you think. Okay. So the reason it was none of the available answers, which Emerald, hey, good work. Right? 10 kilograms is 10 kilograms regardless. Well said. And so the reason to use a trick question really is just to kind of stress the importance of it, of this concept, with which I think can feel like a pretty easy concept with a little bit of practice or background or just reading whatever it is. And my advice is just remember when you're thinking about mass is that mass is a property of an object and it's not dependent on anything. Your mass is your mass regardless of what where you are, so it doesn't depend on gravity. It's just depends on what you're made out of, and that's it. So and the units of it are kilograms. So if something is specified as 10 kilograms, then that's its mass. And it doesn't, like something it may take a lot of hay or feathers or any, low density material to total 10 kilograms, but it's still 10 kilograms. Okay. But of course, that does lead to the non-trick question. If I have 10 kilograms of feathers and 10 kilograms of bricks, okay. So, obviously you think of one as being heavier than the other, but when we think of heavy, we're actually thinking about density in this context. So which is more dense? But you know it now. Yep, Maxwell, you're right. It's the bricks. And I didn't wait for other answers, but it was a first one up. All right, so we have that the bricks are the more dense. And I know it doesn't show the answer, but we'll discuss it in the next slide. So they simply have a greater amount of kilograms per volume. It would take less bricks in terms of volume to total 10 kilograms. So just like in this picture, if you imagine this is feathers, even though obviously it looks like hay, you can, have this kind of visual cue of, well, it just takes up less space, less volume to get the 10 kilograms of bricks.
I
Okay,
have a question. So I think
go
in my
ahead.
mind, I was relating mass with like kind of like the bulk, like not so much the actual weight, but like the size of something. So we
Mhm.
can't really say that, right? So the
Right.
mass isn't the weight and it's not the
The volume.
size.
Yeah.
Okay.
Yep. Yeah.
Okay.
Yeah. Yeah. So it just has that really specific definition.
Yes,
It's the
thank you.
yep. Yeah. Yep. And it's the units help, I think, to remember, okay, well, it's kilograms, kilograms are mass. And so it's the way I haven't described it yet, although I don't know if this will sound overly complicated, but what mass is it's like the sum of all the individual atoms. It's like okay, well, what are the things you're actually made out of? And if you went, and you took all those individual pieces, atoms and molecules, and you total them up,
But we
is
can
what?
say weight then because like this says equal mass. So that means the bricks and the hay are equal weight. So it is weight.
Okay, that's a good question. It's something that we touched on when we talked about Newton's laws. Okay, so it's it's such a good question. It's worth going just slightly off track because okay, so weight, I'll put it right here. The weight represented by W is mass, which is m, using lowercase here, times gravity. So you are right that the weight of the feathers and the weight of the bricks are the same, as long as they're both on the same planet. If I took the bricks to the moon where gravity is less, but I kept the feathers on Earth, both would still have the mass of 10 kilograms. But now the bricks being on the moon where gravity is less, where G is less, would have a smaller weight despite having the same mass. You see the difference?
Yes. So it's, yeah, the location, I guess
Yeah.
the other way to say it.
Yep. Weight is location dependent.
Yes. Oh my
Exactly.
goodness. Ooh, thank you.
Yeah. Yeah. So it's like all these terms that we kind of, convolute understandably because, in everyday speech, because they kind of, mean such similar things. But in science, they have this exact definitions, which I'll say, really are necessary, to have those definitions. And I'm sure you can imagine that, but it takes some getting used to. And so this is just a quick summary about why we have these different densities but the same mass. I know the definition of weight is still up there, but it, don't worry about it for now. So our low density material like hay or feathers has a larger volume and a smaller density in order to achieve the same mass. Okay, so the masses are equal, and we know the masses are equal because of this little picture that shows the balance. All right. Now it is the weights that are causing that balance, but obviously these two, you know, piles of objects are in the same place, they're experiencing the same gravity. But it sure takes a lot more or a larger volume of the smaller density material to equal the same mass.
So because they both have the same measurement and they both have the same number of measurement, it's always going to be the same mass.
They'll they'll always have the same, yeah, they'll always have the same mass if they're both specified as having the same number of kilograms.
Oh, okay. And the same
Yep.
measurement, like one can't be kilograms and the other can't be like a different.
Yeah, yeah.
Okay.
Yeah, like like pounds or something. Yep. Yep. Yeah, but as long as you see that same number and that same unit and it's kilograms, that's what that tells you they are the same mass. Yep. Okay. Okay. So enough with size and density. We're going back to the list of planet characteristics with a little question down here at the bottom. And it's which of these, and that's of the five characteristics, is directly related to the distance from the sun? Which is directly related to the distance from the sun? Can someone tell me? Is it size, density, orbital period, rotational period, or orbital tilt? All right. Maxwell Isabel say it is orbital period, and you are absolutely right. And it I was thinking that it really kind of makes sense because we literally just finished talking about density. It's probably going to be the next on the list, right? If you're just sort of thinking about it logically. And the idea here is that although orbital period doesn't mention distance, it's a length of time rather than, a distance. It is directly related, and we know that from Kepler's third law. And I said Kepler's third law out loud a minute ago, but right now, let's go ahead and write down the equation. So this is Kepler's third law as a proportionality, and it's going to be the period. And you know what? We've been using P, not T, so let me change that over. Be consistent. The T does get used for period, but that's neither here nor there. So P squared is proportional to A cubed. And A is that variable that we use, represents semi-major axis, and it's what represents distance from the sun. There you go. Orbital period. So I have another question for you. Okay. And this one I think you will find kind of interesting. So, thinking about orbits and the solar system as a whole, which of the following, and then you got these different pictures, most closely represents the orbits of the planets in our solar system? So, like if I, was sort of like to build a model of the solar system, would it look more like grooves on a CD? This stack of hula hoops. So, but basically a bunch of orbits that all have the same size, but are like, layered up. A space age mobile where I have different size orbits and they're all tilted different directions, or a Japanese steakhouse onion ring volcano where all the orbits do vary in their diameter, but they also vertically stack. And there would be, I guess, a stand-in of the sun for the fire in the middle. Which represents it best? All right. So yeah, does everyone agree with Maxwell that it's the grooves on a CD? Okay. Well, that is excellent work because the other section, nobody got that, which is why I was thinking that, it was more confusing than I thought, but you, at least those that put an answer in chat, seem to understand. It is like that. The solar system is flat, which is kind of the key characteristic of the grooves on a CD compared to these other, you know, representations. And by the way, the answer that everyone thought in the other section was the space age mobile. So, they definitely remembered that, planets have different orbits and that, they're not just stacked on top of each other. But I guess for whatever reason, that other class thought that they were all tilted in different directions, but they're not, right? All the orbits of the major planets are basically in the same plane. They make a disk. They make a flat solar system. And to show that flat solar system, let's take a look at this picture. All right, so this is a figure that shows the solar system. It might, on first appearance, show some pretty tilted orbits that look a lot more like the space age mobile, but that's because it's also including objects that are not major planets. All right. But let's take a look at just the blue rings for now. So the blue rings that represent the orbits of the major planets. We can see the sun at the very center, but then we can see the four closely packed orbits of the terrestrial planets: Mercury, Venus, Earth, and Mars. We then have a gap from Mars to Jupiter, and then we have the much more widely spaced orbits of the Jovian planets, which are the gas giants. Jovian is a term that you will see. And those are Jupiter, Saturn, Uranus, and Neptune. And all 8 of the major planets are almost exactly planar with each other. They make a flat orbital system. And that plane is called the ecliptic plane. And there's only a degree or two off between the orbits, between planets and that plane. But then if you look at, these other red orbits, not only are they more elliptical, which is kind of interesting, they're also obviously tilted. And that's because they are the orbits of dwarf planets. And a characteristic of these dwarf planet orbits is that they don't tend to be as planar. So we've got Pluto, Haumea, Makemake, and Eris being four dwarf planets past the orbit of Neptune. We'll learn about a term that describes any orbital body that is further out in the solar system beyond Neptune, but not too far, because there's another region of the solar system that we'll discuss when we discuss comets that is not covered in this, excuse me, in this section or this chapter. There is actually one more dwarf planet in the solar system. It's not just the one more that's labeled in this figure. It's the only one that is in the inner solar system, and its Ceres. It's actually located in the asteroid belt. It is somewhat tilted, as you can see. Kind of if you look carefully at how the orbit sort of gets closer and further away from the blue lines, representing that tilt. But it is the only large enough body in the asteroid belt to be considered a dwarf planet. Yes, all the red lines are dwarf planets, all the blue lines are major planets. Exactly. And then make sure is it yeah. And and then the dwarf planets shown are not the only dwarf planets. There are more, most of them fairly recently discovered, and all beyond the orbit of Eris. So these are, there's speculated to be many of them, maybe dozens more, but they get further and further away and are harder and harder to detect. So it's an ongoing process of discovery.
So if they're in the same orbit of like similarly to a disk, a CD,
Mhm,
um, I see on here that's the red orbits, the ones
mhm.
that are labeled as red, they're tilted a little bit. And I know the CD is flat.
That's
So
what I was just talking about. Yeah.
I was just a little confused as you're explaining, like I still don't really understand how it's
Okay.
still tilted.
So the the red think about it this way, the red orbits don't count because the question said, which of the following most closely represents the orbit of the planets? The red orbits are not planets.
Oh, I didn't hear that part. Okay.
Yeah, so and it's I could have definitely stressed it more because it's a weird distinction. So a planet, I kept calling it a major planet because I was trying to be more clear, but the technical, really the definition is planet. There are only 8 planets in the solar system.
Okay. I understand now.
Yeah, right. Pluto is not a planet. So yeah. And so that's the key idea is that we have those particular definitions. And it's Pluto, of course, used to be a planet, but it got demoted. Um, and you kind of almost like see here that it's a good thing it did, because otherwise we'd have sort of a weird discussion about planets, right? We couldn't make the same generalizations, and in science, generalizations are helpful because they allow us to make meaningful hypotheses and conclusions. So having this real separate concept of planets and dwarf planets is a good idea. Although I know it was not popular, you know, to demote Pluto. Okay, so with the definitions out of the way, so that I was just, defining the terms of the characteristics, we're now really going to kind of put those characteristics to use. So we're going to use things like density and orbital period to classify the planets, to split them into separate groups. Right? Not doing the activity. So to split into separate groups, let's start by grouping together planets into small, and large. And with all of these groupings, we're going to have the 8 planets shown. And for contrast, we're going to also have 2 representative dwarf planets included. Okay? So, but do keep those separate in your mind that, we're grouping the planet, and then we're just kind of, talking about how the dwarf planets mostly don't follow the same rules, which will become evident. So our small planets, and that all of them are small both in terms of radius and mass. So, there's no such thing as a small planet that is more massive than a big planet. That would take such a drastic change in density that no such thing exists between planets. But the small ones are Mercury, Venus, Earth, and Mars. Okay? And they're quite a bit smaller, often, over 20 times smaller than the larger planets, which are Jupiter, Saturn, Uranus, and Neptune. So clear distinction between small and large. Definitely within the small category are all the dwarf planets, including Pluto and Eris. Here's another way to group planets: density. Okay? So dense, that would be, high density, as compared to not dense, low density. Well, the groupings are the same. Okay? At least in terms of planets. Mercury, Venus, Earth, Mars are the dense planets, right? They have densities above 3.5 times the density of water. Okay? Sometimes, quite a bit higher than that. So make a quick note of that. You'll see it again, but it's worth pointing out that here, all of the densities are going to be greater than, so this is the density of this category, the density 3.5 times the density of water. If you're wondering about why I just suddenly brought up water, W for water, it's because it's really a very common comparison for densities. We often compare densities to water, even in astronomy. And so, it's done in other sciences as well, like chemistry. So that's what we're doing here. We're just using the density of water as a comparison. It's not base units, right? The density of water in base units is, incidentally, about 1,000 kilograms per cubic meter. Don't worry about that right now, but that would be in base units. Okay. The not dense planets, Jupiter, Saturn, Uranus, and Neptune, would all have lower densities. Okay. One of them, in fact, Saturn, has a density that's less than water. The other 3 planets with low densities, here in the not dense category, are kind of like close to water, but slightly above it. So in the kind of the 1.1, 1.3 range. Interestingly, our dwarf planets, Pluto and Eris, fall into the not dense category. And they are denser than the 4 planets, but not nearly as dense as Mercury, Venus, Earth, and Mars. They're kind of in the middle, and they're grouped in the not dense. Okay, here's a totally different way of grouping them, which wasn't one of our characteristics, but is worth mentioning. And that's, how many moons do they have? How many moons do these different planets have? Well, Mercury, Venus, Earth, and Mars, still sticking together as a group, have very few moons. In fact, Mercury has 0 moons. So does Venus. Earth has 1, which I'm sure comes as a big surprise. And Mars has 2 moons, but unlike our moon, they're both really small. So Mars has these 2 little mini moons, but it does have moons. Pluto, interestingly, actually does have 1 moon. Eris has none, as far as we know. I say that because it's such a distant object, and sometimes it's easy to miss that information. We have very few images, and those images are just a few pixels wide. But in contrast, Jupiter, Saturn, Uranus, and Neptune have huge systems of moons. In the case of Jupiter and Saturn, they have over 50 moons apiece. And so they're almost like mini little systems. That we wouldn't call them solar systems because there's no soul, but they are big orbital systems. Okay, big in the sense of having lots of separate bodies. So real key characteristic difference between this group and the other. What about distance from the sun? Well, check it out. We got basically the planets still doing the same thing. So every single time, Mercury, Venus, Earth, and Mars have stuck together as a group, right? Jupiter, Saturn, Uranus, and Neptune have as well, because, well, Jupiter, Saturn, Uranus, and Neptune are far from the sun. We saw that in the figure back when we were talking about how flat the solar system was. Okay, Mercury, Venus, Earth, and Mars are all crowded together much closer to the sun. Pluto and Aries are in the far category. They're way out there. Could we find a dwarf planet, since that's what Pluto and Aries are, that is close to the sun? We could. And I mentioned it before, and it would be Ceres. So we could even, consider that the dwarf planets not only jump back and forth between the blue and the orange group, but they can even split. So they don't follow the same rules, but the planets sure do. We've got our cliques of planets always sticking together. Okay. Now we've been talking a lot about dwarf planets. Let's make sure that we're clear on some ideas about what they are and what they are not. Okay. So a dwarf planet is round, and that's basically what makes it a planet. That's why it's got the term planet in its name, as opposed to an asteroid. Okay. So the fact that the dwarf planet is round is its distinction from an asteroid. Asteroids are not round. And by round, we do mean spherical. Okay. So round, kind of a less technical term, but really specifically, this is a spherical body. Okay. And they are quite a bit smaller than even the smallest of the terrestrial planets, which is Mercury. So it's fair to say that they're pretty small and that dwarf is an apt name. In fact, dwarf planets are smaller than mini moons. Not our, well, actually, yeah, mini dwarf planets are smaller than our moon. Not the Martian moons, those little tiny ones, and not all moons. There are plenty of tiny moons that orbit Jupiter, for example. But of the bigger moons in the solar system, many of them are bigger than all of the dwarf planets, or at least a selection of them. The one thing that really separates dwarf planets technically from planets is not that they, don't group as nicely, not even that they have the tilted orbits, which might seem like a good distinction, but actually that they don't dominate their orbit, which has to do with a rather complicated way of thinking about how many other objects share that orbit. I say it's complicated because it brings up ideas that we briefly touched on when we talked about the James Webb Space Telescope and the fact that it's located at a Lagrange point, because there are asteroids that actually inhabit the Lagrange points of especially the gas giants like Jupiter. So you might think, well, Jupiter's got other things in its orbit, but there's this whole distinction about how those asteroids that are in the orbit of Jupiter are there because of the gravitational pull of Jupiter, where in the case of Pluto, there's other bodies that share Pluto's orbit just because they're not affected by the gravitational pull of Pluto, and they're just able to share that same orbit. Pluto's just not a large enough body to have cleared out its orbit, is one way it's sometimes described. And that's really the extent of like how detailed you need to understand that there's something about, dominating or clearing the orbit is what separates dwarf planets from planets. So looking at the table here, we've got some sizes of dwarf planets. Okay, so well-known dwarf planets: Ceres, the only one in the asteroid belt; Pluto, Haumea, Makemake, and Eris. We can see that their sizes are quite small compared to the Earth. right? So we're looking at planets here that are sometimes less than 10% the diameter of Earth and always less than 20%, which would be 0.2 written as a decimal. In contrast, our moon is more than a quarter the diameter of Earth. See how the moon is 0.27? So our own moon is over a quarter the size of the planet, of our planet. Okay, but none of the dwarf planets are that big. Mercury, the smallest planet, is, less than half the size of Earth, but still noticeably larger than any of the dwarf planets. The densities, they run low, but although you won't see the number in the slides, you can look up the number in the book, and I've mentioned it. They are higher than the densities of the Jovian planets, Jupiter, Saturn, Uranus, and Neptune. Okay, so these values here, all compared to water, as I mentioned before, range from the lowest at 1.9 to the highest at 3, right? Represent the density, typical densities of dwarf planets. This is middle range. And to put it in writing, the density of Jupiter, for example, is about 1.2 times the density of water. And Saturn, as I said before, is actually 0.9 W for water. Okay, so notice that 1.2 is smaller. Okay, so you've got kind of the real low density planets, then you've got dwarf planets in the middle, and then you have in particular, the terrestrial planets. So this one right here, with Mercury having a density of 5.43, so very high density, and pretty representative of the other terrestrial planets, although Venus and Mars are not as high. And the moon actually does have a lower density, significantly lower than Earth's, which has to do with some speculation about how the moon was created, but it does have a noticeably lower density than Earth's. Actually, similar but higher than the dwarf planets. So if you're thinking, okay, there's all these different categories of density, yes, but kind of try to work out for yourself how you can group them together, remembering that you've got your Jovian group, your dwarf planet group, you're in your terrestrial group, and if you're going to start including moons, then you're going to start seeing them, especially if you include all of the moons, you'll start seeing those kind of pop up in different, crossing over with other groups. Okay, this is just talking about the structure of the solar system in a reference. Okay, so let's run down through the characteristics real fast. Comparing size, the sun is obviously, by far bigger than everything else. In fact, let me point out that the sun, in terms of size and mass, is 99.9% of the solar system. So the sun possesses 99.9% of the mass of the entire solar system. I know I kind of like said this before, but I think I'd rounded it to 99, but it's 99.9. That means that all the planets total just 0.1% of the mass of the sun. Okay, but still there's some pretty big distinctions, because when you go down in size, you got the Jovian planets way bigger than the terrestrial planets. Right, so you have a difference here of like the size of Jupiter being equal to 1,000 times the size of Earth in terms of its volume. So it really, but of course Jupiter is the biggest of the Jovian planets. But still pretty big distinction. And then we just saw some actual numbers to separate terrestrial planets from dwarf planets. So we can continue to have some pretty big size differences, but none of those differences are as drastic as the first step from the sun to everything else. All right. The other objects that put up the size range, Well, before we go over the answer, let's do what the slide suggests and have you tell me. So, what do you think could fill in this, kind of the rest of the solar system? What are things that are smaller than dwarf planets that are out there in the solar system? What do you mean by three? I just want just like a description of things that are smaller than dwarf planets. Ah, terrestrial planets. Okay. Oh yeah, you're just okay. One, two, yeah. So, but there, I want something that is other than is on the list. So, what could we add to the list that's down here? I know it's kind of, the directions are a little bit different, but what could we add down here that isn't already here? Okay, Isabel suggests stars, but stars actually wouldn't be down here because they're too big. Stars would be, the size of the sun, kind of closer to the sun, and they wouldn't be in our solar system. So we can't add stars because we're just talking about things that are in our solar system based on size. Okay, hey, that's closer to what I was kind of thinking, and there are some key things. Okay, Maxwell says comets, meteors, asteroids. Yeah, and it's worth pointing out, Emerald, that meteors, it's are the event or the streak in the sky that's caused by an asteroid entering our atmosphere. So the term for the object is an asteroid, and the streak is the meteor. I know it gets confusing because it's like, wait, aren't those like interchangeable? But no, the actual the object is not called the meteor. Yeah, yeah, you and many people. We will cover that really specifically when I think it's the very last chapter on the solar system. So that's why I almost hesitated to even bring it up, but it was worth mentioning right now. Because there's also meteorites. What is that? Well, we'll worry about it later. But maybe you know. Okay, so good. But we got asteroids, comets. Those are all going to be on the list. So let's take a look. Okay, so we've got moons, right? Which maybe just didn't cross your mind, but if you thought about it, well, certainly, and and we know that they're comparable to dwarf planets. Asteroids, something called a KBO. I'll talk about that. Comets, the comets are going to be consistently smaller than dwarf planets, moons, asteroids. All right. So is there some crossover between asteroids and comets? Absolutely. So they're not strictly smaller, but on average, they definitely are. So your average asteroid is bigger than your average comet. And then finally, rocks and dust. There's a bunch of just tiny little pieces throughout the whole solar system, things that aren't just individual molecules or gas, but actually little chunks of things. And they're all throughout the solar system. Okay? So what is a KBO? Well, I'll write it out here, but we will see it. It is a Kuiper, named after the person that first discovered this region of the solar system. Kuiper belt. Okay, and then the O is object. So a KBO is a Kuiper belt object. And the Kuiper belt is a lot like the asteroid belt, which is much more well known. You've probably heard of the asteroid belt. What you might not know or remember is that the asteroid belt is located between Mars and Jupiter. I mentioned it a moment ago, but that's where it is. Okay. Well, the Kuiper belt is past Neptune, and they're both belts full of asteroids mostly, and dwarf planets, with just one dwarf planet, Ceres, located in the asteroid belt, but many dwarf planets, including Pluto, Haumea, Makemake, and Eris, located in the Kuiper belt. Yeah, Kuiper belt object. Yeah, Maxwell name. All right, so let's carry on. Okay, so here it is, similar to the asteroid belt, but beyond Neptune. That's the best way to describe it. This is a representation of it. Okay, the size of kind of like the dots would not be to scale, but it's just showing where all the Kuiper belt objects will be located. The yellow tilted orbit is Pluto, and the largest white orbit would be Neptune. So KBOs, Kuiper belt objects, are icy and rocky, which separates them from a comet, which is almost entirely icy. And they are objects found in the Kuiper belt. The examples, Pluto, Charon, Haumea, Makemake, Eris, are in the Kuiper belt. Charon, which I have not mentioned by name, is the moon of Pluto. It's Pluto's single moon, which interestingly is almost as big as Pluto itself. So it's almost like they orbit each other rather than Charon being Pluto's moon as we think about moons. Okay, so summary of sizes. I'll actually do this one somewhat quickly because it's all stuff we've already touched over, but have not seen summarized exactly like this. Moons, less than 1 kilometer, as big as 5,268 kilometers. So that's the biggest moon in the solar system, which is Ganymede, but we'll talk about Ganymede later on. It's one of the moons of Jupiter. Okay, so from the very smallest moons at 1 kilometer all the way up to the biggest. And a few other big moons are kind of in this size range. Dwarf planets range from a lower limit of 952 kilometers, which is maybe Ceres itself, I think is the smallest, although I thought Ceres was just above 1,000. So I'd have to look up for sure. But Ceres is one of the smaller ones, but there are maybe a smaller one out there in the Kuiper belt. The biggest dwarf planet by size is there's again these numbers are getting updated and varying in the kind of tens of kilometers with better measurements. Although we do have a very exact measurement for Pluto because of the recent New Horizons mission. But what I mean to say is that the biggest of the dwarf planets is either Pluto or Eris, and there is I know that one of them is considered more massive than Pluto, but Pluto may still be the biggest in size. Asteroids range from tens of meters. Okay, so remember that there's 1,000 meters in a kilometer, so we're talking much smaller. Okay, just boulder size. Okay, large boulder, but just a boulder. To 530 kilometers. So you wouldn't get much bigger than 530 kilometers because any asteroid bigger than this has the potential of becoming a dwarf planet. Because it could become round or it could have formed round in the first place. But this is kind of, the upper limit, and you can get, somewhere between 530 and 952 is where that transition happens. And we just don't have any representative asteroid or dwarf planet in that range because we are, of course, just one solar system. But if you were to survey other solar systems, you could certainly find some sort of body in here and find out, exactly where that cutoff is. But we just know it's somewhere between the two. KBOs, those Kuiper belt objects, have the same lower limit, and they can range up to 100 plus kilometers. Notice kind of this vague upper limit. That's because if we count KBOs that are not dwarf planets, well, then our upper limit is going to be something closer to 500. But if we include the dwarf planets, then it's going to be something over 2,000. And since that category, KBO, is not exclusive to asteroids or dwarf planets. It's a grouping that includes both. Well, technically, it would include Pluto. So then the upper limit of KBOs would be Pluto itself or whatever dwarf planet happens to be slightly larger. Comets, finally, which we are talking about the least. We will save most of our comet discussion for another chapter. Range from hundreds of meters, okay, to which is kind of interesting because I think you could say that they can be smaller, to 20 plus kilometers, so that they do have. It's actually the that's like remember when we had that the slide that showed the scale here. So and they put comets as smaller. It's really because of this upper limit. So comets just don't get that big. They have a much smaller range. And so an asteroid, there are quite a few that are hundreds of kilometers in size, right? And one that's 530. But there are no comets in that size range at all. They max out at 20. Okay. 20 plus, sure, because there are a lot of them and a lot that we haven't discovered. Um, the vast majority we've never seen. But as far as we know, their sizes are pretty strictly limited. All right. So I mentioned before that dwarf planets can be smaller than moons. So what we're seeing here, this is this first kind of bullet point, and we're coming up on break. So let me get to a good starting point. There are 7 moons in the solar system that are bigger than dwarf planets, bigger than any dwarf planet. So we have 7 moons that are bigger than any dwarf planet. Right. So it's interesting, right? So because moons are this weird category. They can really vary and kind of jump around. And if that's bothering you, well, think of it as an interesting tidbit that we will get into later, because we'll talk about the huge variety of moons when we specifically cover Jovian planets. And there are some good reasons why moons vary so much in their size. They also vary a bit in their composition, but they do tend to be kind of rocky and icy like dwarf planets, but they definitely vary in size. There are a lot of moons that are smaller than um, dwarf planets, okay, smaller than 952, and most moons are. Okay, so there's 7 moons that are quite large, but the vast majority of the 200 plus moons in the solar system are smaller than any dwarf planet. Asteroids, well, there are 190 plus moons that are bigger than the biggest asteroid. So, as far as a distinction between asteroids and moons, there are a lot more small asteroids than there are small moons, which is actually really interesting. And I don't have a good explanation of why that would be. And it has really provoked some ideas, which is always happens in astronomy. You see some value, and you kind of think about, well, it doesn't quite fit some kind of model you have in your head or things you've heard about, and then you can investigate it. Okay, so let's finish off with this question before our break, and that is on the right is a table of properties of a planet, and then which grouping would the planet belong to? We're given its mass, radius, its density, and its semi-major axis. And so, would it be, based on these numbers, a terrestrial or a Jovian planet? Okay, I was waiting for a couple answers. Well, thank you, Maxwell, Kylie. Maybe other people are thinking about it, typing right now. Well, Maxwell and Kylie, you both put terrestrial. Are you right? Absolutely. And this just takes us back to all those slides that showed the circles with the different planets in them. And we got our, small size, high density, relatively high at least, and then close to the sun. There we go. All right. Um, Let me just quickly run through this one. Okay. This I really will go fast this one for real this time. We got these compositions: hydrogen and helium gas, rock, and ices. The reason we're talking about these different materials, essentially the building blocks of the solar system, is because this is going to sort of quickly show a explanation of that variety of densities. I've sort of hinted at this, that why the densities vary. Okay. But if you look at the sun is made of just hydrogen and helium. So the sun is entirely made out of that. Well, it's got trace amounts of other materials. The low density Jovian planets are also mostly hydrogen and helium, but they actually do have rocky cores with an amount of rock that is actually greater than a single terrestrial planet, but proportionally small for the Jovian planet itself. But that keeps their density low because they're mostly made of hydrogen and helium. Asteroids are mostly rock with a little bit of ice. And that's in contrast to terrestrial planets, which you can say are almost entirely rock. And we're including metal here with rock. Okay, rock, metal veins, kind of, all the mineral aspects. Dwarf planets are even icier than asteroids, generally because they're further from the sun. So dwarf planets have a large amount of ice. And this is not just ice on the surface, but this is ice throughout the planet. So it's a sort of an ice rock mixture that doesn't exist on Earth and only can exist in a much colder part of the solar system. Most of the moons are also mixes of rock and ice because most of the moons orbit the Jovian planets and have compositions similar to the dwarf planets. Our moon would not fall, into this typical breakdown between rock and ice. It would be much more rock. Kuiper belt objects, which would include dwarf planets, but also include all of the asteroids in the Kuiper belt, on average are even icier. So think of the difference here between dwarf planet and KBOs, as KBOs being, just all those things further from Neptune. So excluding Ceres, but including a bunch of asteroids that orbit at the same distance as, say, Eris or Haumea. And those on average have greater contents of ice. And by the way, the poster child of pure ice would be a comet, which would have trace amounts of heavier elements, some dust, but almost entirely ice. All right. So we'll take a 5-minute break, which will take us up to 9:15. Then we'll come back and finish up these slides. So I'm going to go ahead, pause the recording, mute everything on my end, and check in all with you when I get back, including checking the chat. All right, so continuing with chapter 7, we have that moons orbit planets, dwarf planets orbit the sun. And then what is the most important difference between asteroids and dwarf planets? Spoke about this a while back. What is it? All right. I got to vote for one. Okay. A few of you are saying that the difference is what they are made out of. Turns out that it's actually their shape. which if you maybe take a step back and reconsider, you could see why. Because when we talked about asteroids and dwarf planets, we saw that they had crossover, right? They weren't made of very different things. Sure, asteroids tend to be rockier, but that was not a key difference. The key difference is that dwarf planets are spherical and asteroids are not. That is the defining difference. All right. So their shape kind of almost seems like one of those answers that couldn't be right at first glance, but it absolutely is. Okay. So hopefully that makes sense. All right. So let's get to the last part of the chapter 7 slides. Solar system history. How did the solar system get this way? We've talked about these general rules of the solar system, and highly recommend reading over the textbook, looking at the figures in the textbook for a lot more elaborated ideas, because I feel like we have really just touched on them here in the slides. But to explain how the solar system came about, we have a model that is definitely been supported by lots of recent evidence, and including our study of other solar systems, which has been a burgeoning field of science. And that's the idea that the solar system originally existed as a cloud of gas, a solar nebula. We'll talk kind of about what properties this nebula would have had when we talk about the evolution of stars. And at some point, that solar nebula, called a solar nebula because it's going to create a sun, a star, that is, at some point, it collapsed under the influence of gravity. And that would have been a gradual but accelerating collapse, taking um, hundreds of millions or even billions of years, depending on the sizes involved. And as that nebula shrunk, it also flattened and it began to spin faster. And the spinning motion and the flattening are inexorably connected. So the fact that as the nebula collapses, it has to spin faster due to conservation of angular momentum, that causes it to flatten more. And the flattening happens because of the random collisions that are occurring all of the time, in this case, under conditions of rotation. And so as random collisions happen, but rotation is present, the direction that becomes predominant is going to be a direction parallel to the plane of rotation. And this is just not a that statement would not in any way be specific to astronomy. You could show the same behavior with a terrestrial experiment, with a fluid. It's just fundamental physics. As the nebula formed a disk of matter, there was a concentration of that matter near the center. I bet you can guess what that concentration became. In our case, it became the sun. In general, it becomes a star. And that's the vast majority of the matter, as we know. Some 99.9%, just leaving 1/1000th of the total matter left over as a sparsely populated disk. So just a little bit of leftover dust, if you will, which is moving around that center concentration of matter. But all of those leftovers, all of that cooling gas and coalescing rock and pebble and larger objects that will then start to form the planets is very important to us because that's how a planet like Earth came about. But before a stable system of planets like the ones that we have been discussing, would have fully resolved. There is a stage in solar system history, including, as far as we know, in our own solar system's history, where we had the sun basically at its current size in a stage called a protosun, which would have been just before the ignition, for lack of a better word, of fusion. So right at the moment, right kind of as the sun started to become an actual full source of energy, at least the energy coming from fusion, although there would have still been a great deal of energy coming from the protosun, but coming from gravitational contraction. And then that when that comes to an end, the energy begins to come from fusion itself, which is a beautiful, fascinating story about energy and physics and atoms, but one we'll talk about when we talk about the sun specifically, because of course the sun deserves its own chapter. Solid particles, the ones that were the disk, which of course all originally started as the molecules in the nebula, are condensing as the nebula cools, and that's a general truth and a gradual process that things are cooling throughout this, all four of the stages shown, and that cooling always allows for bigger and bigger things to occur. The process of building up the sun could be described a bit differently, but certainly everything that's happening in the disk around the sun is all about cooling and clumping. And this stage of the solar system is dominated by something called planetismals. Planetismals are just the precursor to planets. They share a lot in common with planets, and they are the building blocks of planets. In fact, you can think of a planetismal as being basically, if you saw one, just like a dwarf planet. It would be in that size range, you know, smaller than a typical terrestrial planet. A planetesimal would be round, although there would be plenty of kind of, things that we would call asteroids, which may or may not be categorized as planetesimals. But there are many of them. They occupy shared orbits, crossing orbits, and they're colliding with each other regularly, at least on a geological timescale, during this stage of the universe. And when I say a geological timescale, I basically am pointing out that this whole process of planetesimals becoming planets would have taken hundreds of millions of years. And that's not a huge portion of the overall age of the solar system at 3.5 billion, but a a significant chunk of time, certainly by our own scale. Okay. So what are some evidence of this type of solar system history, this model for the solar system's history? Well, one is that planets orbit in the same plane, and understanding how that could have come about fits this type of process very well. And to elaborate on what are planetesimals, they are small hunks of rock formed in the early solar system. By small, of course, we mean, often kilometers in size. And they're going to be gravitationally interacting with each other. And in what way? Well, I may have given it away when I talked about them colliding. So I'm going to give you the answer, but you're welcome to think of it. And maybe some of you have already put it in chat. But they're going to get pulled together. And suffice to say that that's just because gravity is an attractive force. Remember, gravity cannot push things. It can only, pull things. Gravity is always attractive, never repulsive. So the interaction here is that they're going to get smashed together because of gravity, and that can lead to the formation of larger objects, almost like a snowball picking up more snow as it rolls downhill. Okay, but some different physics, but kind of same general idea. As planetesimals can form bigger and bigger planets. And as they did so, the planets that eventually formed were those that were far enough apart that they could avoid further collisions. And what's happening during this stage of the solar system, where all of these planetismals are smashing together, is a huge amount of energy being released. And we're asked here, how does an object, or how do objects' temperatures change when they are rubbed together via friction? Well, rubbing, smashing might seem like different things, but that's kind of what we're talking about here is, planetismals coming together and converting some sort of movement energy called kinetic energy into heat, which of course would cause a, again, giving you the answer, an increase in temperature. So this is just simply things are heating up. And sometimes, if you're wondering, it's certainly assumed that the planetismals didn't just have, head-on collisions, but would have had some sort of glancing collision or just kind of a gradual approach to each other, where you could think of really the process being more like friction and happening over a slow period of time. Often, the gravitational interaction between two planetismals, which would cause them to, become one bigger object, would really have been them orbiting each other in an orbit where the friction between them, kind of like the tidal friction that exists between us and the moon, would have been so great because of the initial separation distance that they would have just gradually pulled each other apart. So you'd imagine two sort of like, moon size, moon looking objects, probably with a lot more active lava flows on their surface. Since of course the moon has none, right? But so these like volcanic but moon sized objects orbiting each other at very close distance, at least, comparative to their size, maybe just a few diameters apart, with a trail of matter between the two, almost like a tail connecting them, because they're literally pulling each other apart as they gradually spiral inward to become one object. And then that whole process would take tens of thousands or, hundreds or even a million years until it would just become one big molten clump. So really kind of that's what a collision more often was like, although, direct collisions were possible. All right. So that's where that idea of, warming is happening as, the surface of a world is sort of sheared off due to extreme nearby gravity. And it's specifically kind of that tidal effect, which would be the varying gravity across the surface. And further evidence for planetismals, which I touched on a minute ago, are the current composition of the planets, which shows similar materials throughout the solar system, and differentiation of those bodies, and those would be the bodies of the planets. We'll talk just a bit about what differentiated is. We also have leftover planetismals. That's what we think the dwarf planets are, and many of the moons are planetismals that never clumped up with others and are just got gravitationally flung further enough out to become a dwarf planet in the Kuiper Belt, or got captured by a fully formed planet to become a Jovian moon. The age of the objects in the solar system is also evidence of planetismals. So we see that the solar system has a common age. So there seems to suggest a key transition from a bunch of earlier building blocks that kind of all started, clumping together at one point, rather than say, Jupiter forming first and being much older than everything else. Instead, we have a pretty much shared age. So I said that I would clarify what differentiation is, because it's not a word that is, has an obvious definition, and the definition in astronomy is specific. So when you have a hot, newly formed planet, it undergoes differentiation. Okay, but what is it? It's the creation of layers in the interior of the planet and the core and the atmosphere. So essentially, it is the layering of a planet. So when a planet is differentiated, it has a denser core, a less dense outer core and mantle, a usually lighter crust, and then the lightest material, the lowest density material, the gases form the atmosphere. And so there's that clear differentiation between the layers of the planet, like the layers of an onion, right? And we see that in planets and dwarf planets, and we don't see it in asteroids. So the way we would, form a sentence that involves asteroids and differentiation, we would say that asteroids are non-differentiated bodies. Why? Because they never got hot enough. They never got to a molten stage where they were able to differentiate. And that has to do with their size and the strength of gravity that's related to that size. So they never had, the denser material sinking to the core and the lighter material rising to the surface. All right. So for molten planets, planets that had a molten stage, like we assume all the planets had to have, by definition, this is our understanding of how planets form, and this would include Earth. So, in other words, Earth at some point would have been entirely molten. The whole planet would have been what we think of as lava, right? Lava and magma. There would have been no solid rock, no cooled crust, right? The whole planet would have just been one hot mess. And during that phase, the heavy materials, due to the influence of gravity, would be sinking towards the center, and the lighter materials are floating to the surface. Okay, as the planet cools, that then locks in that lighter material near the surface and the denser material at the core. Okay, and is Earth like totally cooled to a solid? It isn't, right? Earth still is molten inside, but it's cooled enough that the differentiation is still locked in place. So when differentiation occurs, the density of the terrestrial planet does what? I do want you to think, oh, shoot, I meant to not show you. um, so, right. So if you take a look at this, that what I had intended you to think about, and you still can, even though I gave away the answer, which is what happens to the density. And the point is that it doesn't change. So differentiation doesn't change density because density refers to the object as a whole. Differentiation is just layering. It's still the same object. It still has the same total mass. It still has the same total size. All it's done is layer up. Okay? So that process of creating layers does not change density. It would change density of individual layers, right? If before the core was the core, if it was just a mixture that was uniform throughout the whole molten planet, then it would have a lower density than it has now because it's got denser as all the heavier material has sunk. But that's just the core. The whole planet has not changed density. Right? So same amount of material, same volume, same density. That's the idea. So if you're paying attention to what I just said, this should be easy for you, but let's see if you can answer. Which of the following places is most likely not to be differentiated? Get your options there. Asteroid, Earth, Jupiter, Venus, Ganymede. All right. Elizabeth says one. Maxwell agrees. So does Caleb and Kylie. And you are all right. Because that's what I was talking about, right? They're too small. They're too small to be differentiated. Okay. Ganymede's big enough. It is. Right. Being a moon is not you know, any reason to not be differentiated. Although some moons aren't, because some moons are so small that they are not, as I mentioned before, at least the smallness of some moons. So, you know how in support of the theory of planetismals, as well, I should say, the idea of planetismals as part of our theory of solar system formation, what it was that there are leftovers. Well, these are all good candidates for leftover planetesimals: dwarf planets, moons, asteroids, KBOs, comets, and just rocks. All right. So this is technically not a separate section, but just to tie in with the history of the solar system. How do we come up with dates for the solar system? And there's going to be an idea here that I'm going to sort of not spend a ton of time with, but you're going to get some practice with it in the homework. So and you can, look into it more. And that's something you'll see in a minute, is going to be radiometric dating. So, but first, let's talk about one way that the solar system has its age estimated, and that's crater counting. So often we can look at objects in the solar system and estimate the age of the surface of that object by the amount of craters. And we're not using that so much to find the age of the whole, in this case, our moon, or to use this method to find the age of a dwarf planet, but rather just the age of a particular region, because we're interested if there was some change that happened on the surface at some point, and when did it occur? And that change could have been because of volcanic activity. It could have been because of, maybe some atmospheric effects. If it's one of these few worlds that has an atmosphere. As an example, if we look at the moon, we can see a section where it's smooth. There's very few craters, and we can see a section with a great number of craters. And if crater counting can help us tell age, what do you think would suggest the greater age? The smooth section or the heavily cratered section? Which one is older? In this case, for the moon, which surface of which region of the moon is an older region? So let's see. Left is the smooth one, right is the heavily cratered. Okay, so the one on the right, the heavily cratered, everyone seems to think is the older region, and that's absolutely right. So heavy cratering is associated with greater age. So in this case, we would say that the smoother part of the moon has been, created or resurfaced more recently. And we think that what has happened in the case of the moon is that there has been volcanic activity in with these basically large lava plains called lunar mares, or maria for a single one. And this occurred for a total of 2.7 billion years, but ceased 1.2 billion years ago. And there's been no volcanic activity since. Now the moon is entirely volcanically dead. There's no eruptions, no release of heat. It appears to be cold and completely cooled throughout. But there, strong evidence that there was volcanic activity, and the most compelling evidence is what we're looking at, that there are these big smooth sections, and we can date them because of the amount of cratering. So that cratering counting as a method of dating is very convenient, because all you need is just a picture and you can look at how old your surface is. But how would scientists be sure? How could they really know, what the number of craters and how does it relate to ages? Well, they would need some other measurement to calibrate or confirm the relationship between crater and age. And that's what scientists have done. And it's turned out that craters can be a quite reliable method for estimating age for a number of reasons. But really, the confirmation has been with a different dating method, and that is related to an atomic process called nuclear decay. Okay. And so this is also called radioactive decay. And this is where the nucleus of an atom changes over time because of an unstable nucleus. Right. So I'm going to run through some of the background physics here, just at a good clip. And both because, I'm interested in getting through it for our section, but just this is, what I had planned to do in the first place. I did it with the other section as well. Um, there's only time for so much. So inside the nucleus of an atom, well, there are, to give it away, protons and neutrons. No electrons inside the nucleus. The electrons orbit the nucleus. Right? If you remember how the model of the atom looks. And if we look at an example nucleus of an atom, it can change into another type through this aforementioned process called radioactive decay in a number of different ways. Really, if we're being technical, at least 4 different ways, but 2 that are most important. And there's 2 we're going to discuss in this class. And one type of radioactive decay involves a neutron becoming a proton, and this is called beta decay. Okay, and it involves the release of a tiny particle, but no change in the number of neutrons and protons. So no neutrons or protons, which are much bigger than the tiny particle that I mentioned. By the way, the tiny particle is, in this case, an electron. There's also another version of beta decay where the tiny particle is something called a positron, but don't worry about it. But here, going from a neutron to a proton, what we care about is that the number of neutrons and protons stayed the same. The other key type of radioactive decay, and the only other type that you are responsible for, is the release of 2 protons and 2 neutrons, which we see kind of circled here. And that type of radioactive decay is called alpha decay. And we see that unlike beta decay, some, significant piece leaves. So the total number, just to summarize, the total number of neutrons and protons in beta decay did not change. But in alpha decay, it did change, and it was decreased by 4, because 4 total proton or neutrons came out of the nucleus. And the collective term for anything that's in the nucleus is a nucleon. So we would say that 4 nucleons were released. So neutrons and protons are nucleons. I say that carefully because neutron and nucleon sound pretty similar. And so it's easy to sort of mix the 2 up. These types of decay, whether beta or alpha, happen slowly. Okay? They're completely random processes. Not all atoms undergo them. In general, only the larger atoms or what are called unstable isotopes undergo radioactive decay. So you could basically safely say that most things you would find are not radioactive. They don't go through this type of process, but there are plenty of naturally occurring elements and isotopes of those elements that do undergo decay. All right, but decay, generally speaking, is very slow. Are there such things as, fast radioactive decay? Yes, but usually for things that are produced from very high energy processes, like, things that are being produced in stars and novas and, um, you know, uh, neutron stars and things like that, and things that are man-made in laboratories. When we talk about radioactive decay, what we care about even more than knowing the 2 names of the most common types is the concept of the half-life. And this is what you're most likely, to kind of to see, you see as a numerical problem in the homework, but also that, you're most likely to be asked a concept question about, say, on tomorrow's quiz. And what is the half-life? Okay. Well, the half-life is the average time for half of all atoms of one type to change to the other type. So we take an example of an element called rubidium, and the isotope that we're interested in is 87. And by the way, when I refer to isotope, an isotope is just a type of an element. So when you have, a named element from the periodic table, like gold or carbon, or in this case, rubidium, there are different possible numbers of neutrons that can exist inside the nucleus. The number of protons is fixed and defines the element and its name, but the number of neutrons can vary. And the different number of neutrons are called different isotopes. So in this case, because of the number of neutrons, this version of rubidium is rubidium 87. And you might have seen that with like uranium, for example. There's uranium 255 and uranium 258. Those are two different naturally occurring isotopes of uranium. And the reason that one is 255 and one is 258 is because the 258 has three more neutrons than the 255. They both have the same number of protons. I think it's 112. Okay. And I don't know how many protons rubidium has without looking it up. Okay. But this is a unstable element or unstable isotope. And it decays very slowly, unbelievably slowly. It has a half-life of 48.8 billion years, much longer than the age of the universe, but still gradually it's decaying into a different element, strontium 87. Okay, so it's changing from rubidium 87 to strontium 87. And what's interesting is that since both of them are 87, we can actually tell what type of decay this is because 87 is that represents the total of nucleons. And if it doesn't change, then we know this has to be beta decay, which is kind of cool. But let's just focus on the number for now rather than the type of decay. And to drive home the idea of half-life, if it took 48.8 billion years for half of the rubidium to decay, well, then after another 48.8 billion years, or 97.6 billion, right, just the 48.8 times 2, you're going to have 1/4 rubidium. So you'd say that 1/4 of the original rubidium remains, and 3/4 of it has decayed into strontium 87. The product of the decay now is the majority of the population. If we go 3 half-lives, which would be another 48.8 billion years, now we only have 1/8 rubidium and 7/8 strontium. If we go another half-life, which is another 48.8 billion years, which also would put us at, at an unbelievable point in the future. Well, not unbelievable, but at a drastically different universe than the one today, we would have 1/16 rubidium. So by the end of each half-life, half of the remaining atoms have turned into their daughter elements. So the daughter element in this case is strontium 87, also called the product of the decay, or the decay product. So here's the question for you. All right, so a rock sample returned from the moon contains 7 times as much argon-40 as it does potassium-40. So why are we talking about argon and potassium now? Because this is just another example of decay. Argon is decaying into, or the other way around. Yeah, the other way around. Potassium is decaying into argon. So if I read the next sentence, if potassium-40 turns into argon-40 with a half-life of 1.3 billion years, approximately how old is the rock? You tell me. All right, Lisbeth says 4. Caleb agrees. for 9.1 billion. Maxwell's also agreeing. Number 4 is the option. Rommel as well, or Rommel. All right. Are you all right? Did you all get it? Let's see. You all thought it was 9.1. Interesting. Let's see what happened. So did you do 7 half-lives? Is that it? Because you take 7 times 1.3, is that where the number came from? Uh, I don't feel like doing it in my head, so excuse relying on the calculator. Yeah, okay, cool. So that's an easy mistake to make. Let me see if I can explain why it's a mistake. Okay, so we're told that there's 7 times as much argon 40 as potassium 40. Well, that means that the total is 8. In other words, there's 1 potassium 40 for every 7 argon 40. So the way we could write this is we could say, 1 of the, argon and then 7 of the potassium. I'll check the chat in a second, just a second. So we'll say POT. All right. So then the total in this case, just for, whatever each chunk is, would be 8. So in other words, we could say that 1/8 is argon. So we have 1/8 is, AR, and then potassium would be 7/8. And I could use, I guess, the elemental, uh, representation of potassium, like you see on the periodic table, but it's K. It's kind of confusing, right? But so I'll stick with POT for potassium. So that is our fraction. 1/8 argon to 7/8 potassium. 7 times as much. Oh, did I get it backwards? Whoops. Yeah. Whoops. So let me switch them. So let's do that. I went to look up and I'm like, wait, I gotta switch them. Quick fix. So seven times the argon. Yeah, because I want to have the argon becoming the potassium. I don't know why. And then 1, yeah. So 1 time that, because the potassium is decaying into the argon. So then we can just switch our numbers over here. I'll switch the names, just the numbers. So then you have 7/8 argon to 1/8 potassium. Yeah. Okay. So hey, Emerald says it makes sense. Yeah. So that's the breakdown. And this is such an easy mistake to make. I see it all the time. And there are ways that it can be described to sort of make it more clear. Like if this sentence said a rock sample returned from the moon, contains one eighth, its mass in argon or sorry, well, 7/8, its mass in argon and 1/8 in potassium. You probably were like, oh, okay, there you go. It's all about eighths. Well, an eighth is how many half-lives, and then you'd be able to say, okay, well, it's just going to be, the 3 half-lives because, you get a half after 1 half-life, a quarter after 2, and an eighth after 3. So that's basically what when you see the eighth, you can just think 3 half-lives. But to get to the idea of eighths from this sentence can be tricky. And that's why I wrote it out like this, where I said 7 to 1, and then you just take that sum, and the sum is 8. So just remember to do that if you see half-lives represented in this way. Which, to be fair, is a natural way of kind of describing it, 7 times as much of something, but it does require that extra step of thinking. So hopefully, yeah, does make sense to everybody, including well, obviously Emerald, but other people as well. All right, and I think that will basically wrap things up. Let's check if there's anything else I want to say. Yeah, this just is the breakdown. So showing that after 0 years, it's all potassium 40. After 1.3 billion years, it's 1/2 potassium 40. After 2.6, it's 1/4. And then after 3.9, it's 1/8. And that would, mean that 7/8 is argon. And I say mass like not like the whole rock is composed entirely of potassium and argon, because that wouldn't be the case. Rather, than just be like a small amount overall. But if you were to separate out, just the part that started as potassium, then that's what we're talking about. All right. So then, the idea is that this radiometric dating, as I started off with this whole concept, is a way of confirming the age of the solar system. It can be used independent of cratering, of course, right? It's not just meant to support cratering, although that's a great use of it. But it's crucial for understanding the age of the solar system, and that can lead to understanding that some the oldest rocks are 4.5 billion years old. So I guess I just realized that I said 3.5 before. So please excuse the slip up. The solar system is 4.5 billion years old. Said the wrong number before. So that's kind of, how we can find out the overall age. So that's when, planetesimals were around 4.5 billion years ago. And then the planets started forming around that time. So there you go. There is chapter 7.